So another mathematician named Leonard Euler, whose face we could also look at, came up with a generalization of Fermat's little theorem. And what it basically does is remove the assumption that P is prime. So to sort of make sense of this, consider that if this is the statement of the theorem. But if n is equal to P for P prime, how about this? How about we just say that if n is prime? If n is prime, then phi of n is equal to n minus 1. So remember, this is the totient function. So this is Euler's phi function. And just to remind you what this does, this is just the phi of n is the cardinality of the set of elements A, which are in Zn. So Zn is just the numbers from it's 0, 1 up to n minus 1. So phi of n is the cardinality of the set of A in this set such that the GCD of A and n is equal to 1. So these are the elements in Zn that are relatively prime to n. And so in class we proved that I guess we didn't prove this. We proved that if n is equal to p times q for p and q prime, then phi of n is equal to p minus 1 times q minus 1. So this is an important fact, and we're going to need that later, but an even simpler thing is true, which is, whoops, sorry, I lost a comma. If n is just prime, then phi of n is equal to n minus 1. So why is that? That's because this is just the things that are the things in this set of which there are n elements, right? There are n things in here, and if we restrict our attention to the elements in this set that are relatively prime to n, that's going to be all of them except for 0, because the GCD of any number and 0 is that number. So 0 doesn't come along, but everything else does. And so that is the set of n things minus the 0, that leaves n minus 1 things. So if n is prime, then what is Euler's theorem saying? Euler's generalization of Fermat's little theorem is saying that a to the n minus 1 is congruent to 1 mod n. So, and this assumption will always be true as long as a is non-zero. So that's why I say generalization of Fermat's little theorem, because if n is prime, this is just saying exactly the same thing as Fermat's little theorem. But it also gives information when n is composite. So therefore, we call it a generalization. So let's give an example of using this. I'll scoot this stuff down. All right, so let's pick some values. Maybe n is equal to, what's an interesting composite number? How about 3 times 4 times 7? Let's do that. So what is that? 12 times 7, which is 84, right? Because this is 12 times 7 is 70 plus 14 is 84. Then phi of n is going to be equal to, so an easy way to do this is that it's going to be, I'm going to use this formula for computing phi of n. Maybe I'll just write the formula. Or I'll use it and then I'll give the rule. So this is going to be 3 minus 1 times 4 minus 2 times 7 minus 1, which is equal to 2 times 2 times 6, which is 24. Okay, and how did I do that? It's because I know this rule, which is if n is factorized as a product of primes to certain powers, dot dot dot, p to the k, e to the k, then phi to the n is equal to a big product, this is the big product sign, as I goes from 1 to k of p I to the ei minus p I to the ei minus 1. And I'm sure you can find a proof of that somewhere. I'm not going to give a proof, but this is the rule that I'm applying here to compute this value. And let's just go back to the notebook and see whether or not it's true. So let's say n is equal to 84. And we can also confirm that I didn't just do something incredibly dumb. Let's say factor 84. And yes, it's 4 times 3 times 7. All right, and so what is phi of n? Phi of n is going to be, let's call this the RP for the things relatively prime to n. So this is going to be a for a in the range from 1 to n. So that's just z. It's zn throwing out 0 because we know that 0 is a hopeless case, so we don't need to worry about that one. If, oh man, GCD. So import math, math.gcd 4 and 5. Let me just see if this, I'm going to pause the video and figure this out. Hold on. Okay, I just implemented GCD. This is Euclid's algorithm. So we'll say if the GCD of a and n is 1. Okay, so let's look at the set RPN. So what this is what we call Z84 star. So these are the elements that are relatively prime to n, and we can check out the cardinality of that set. What is it? It's 24. And what did we get using the formula? 24. Okay, so that is that's phi of n. So Euler's generalization of Fermat's little theorem is saying that if we take anything, we're relatively prime to n. So in other words, a has to be in Zn star, like it has to be one of the things in Rpn. Let's look at Rpn again. So if you take anything in here and you raise it to the 24th power, let's say Vn is equal to just the length of Rpn. So let's pick one of these things, like how about 29? So what is 29 to the Vn power mod n? And you have to be careful about order of operations here. 1, and I hate the fact that that L is there, so let's do it like this. Okay, and it doesn't matter as long as if you pick any element of Rpn, so let's just pick one. So how about Rpn, the 13th element? I don't even know what it is, but this is always true. So that's what Euler's theorem is saying. So something kind of there's an interesting consequence of Euler's theorem, which is, let me just scoot all this stuff down. So could say this is a corollary if you're feeling egg-headed, but let's just say that it's a consequence. Then a to the r is congruent to a to the s mod n with these assumptions. So you know, if the GCD of a and n is equal to 1, then a to the r is congruent to a to the s mod n if r is congruent to s mod phi of n. So let's give an example. So we know that 29 is you know, it's in what we're calling RPN, so it's relatively prime to 84, and so phi of n is 24. So let's pick two elements that are congruent mod 24. Like, what should we use? So 5 is congruent to 29. That's kind of a weird coincidence. Let's not do that one. So let's say 10 is congruent to 34 mod 24 if n is equal to 84. So the case that we're working with here. So it should be the case that 29 to the 10th power is congruent to 29 to the 34th power mod 24. So let's use the computer to check that that's true. So is it true that 29 to the 10th power mod n is congruent to 29 to the 34th power mod n? True, right? And the reason it has to be true is the following. We give a little argument that it's true. So it's because we can sort of work it out symbolically, aka prove it. So let me just push this stuff down. This thing is going to be important for understanding RSA. So let's see why it's true. So this says if R is congruent to S mod phi of n. So what's the proof here? So what does it mean for two things to be congruent mod phi of n? That means that R and S have the same remainder mod phi of n. So you know, R is equal to Q times phi of n plus some remainder. Let's just call it R, okay? And let's look at this in more detail. So this is the same thing, or is congruent to, is what we mean. Q times phi of n plus R. And now let's just play around with the laws of exponents. So this is the same thing as a to the q times phi of n times a to the r, which is the same thing as a to the phi of n to the qth power times a to the r. Okay. But look at this. So Fermat's little theorem, Euler's theorem tells us that this is just 1. So this means that you have 1 to the q power times a to the r, and of course 1 to any power is just 1. So this is a to the r mod n. All right. So in other words, the power a to the power, the only relevant thing is what the remainder is mod phi. So this assumption R is congruent to S, that just means that S has the same remainder. So, you know, there will be some other quotient here. We could call it P, I guess, times phi of n. Oh, this is not congruence, this is equality. Phi of n plus the same R, because they are congruent mod phi of n, and that's what it means. It means that they have the same remainder. And so by a similar argument, a to the s is also going to be congruent to a to the r, and therefore they are congruent to each other. So this can be very useful. You can quickly evaluate ridiculous things that it doesn't seem like you should be able to evaluate by hand, Like, let's just look at an example. So suppose we want to know what 3 to the 1711th power is mod, make up a number here. Let's use just 84. So we've been working with this one. So how can you do this? Well, you just figure out, you have to sort of reduce, this power mod 24. So how many times does 24 go into, let's see, so 1711 divided by phi of 84 is equal to, I'll do it here, 1711 divided by 24 is 71. Okay, so that, what is that? Oh, sorry, I want mod, duh. Mod 24, which is 7. So this is true but irrelevant. But we can say that 1711 is equal to 71, that's the quotient, times phi of n, plus a remainder of 7. And so that means that 3 to 1711 is congruent to 3 to the 7th, and that is much easier to evaluate. In fact, have we done this before? So let's figure this out by hand, just because it's good practice. Okay, I'll push this stuff down. So let's start with something we know. So I know that 3 cubed is 27, and mod 24, this is mod, mod phi of n is mod 24 here. So mod 24, this is just 3. Oh, that's very convenient. So to get 3 to the 6th, I can just square what I had before. So this is congruent to 3 squared, which is 9. And now if I want to get 3 to the 7th, I just multiply both sides of that equation by 3. And so that means 3 to the 7th power is congruent to 27, but we've already said that this is just 3 mod 24. And so we've solved the problem. So just by hand, we figured out that 3 to this very large power is just 3 mod 84. Okay, so this is an important part of how RSA works, and I'll say more about that in the next video. But before I go on, let me prove Euler's theorem. And if you don't care about the proof, then you can stop watching now. I'm going to keep scooting. Okay, scoot a little bit more. Basically, the proof of this is the same as the proof of Fermat's little theorem. So first we look at, here, proof. Look at Zn star. So, this is just the set of things that have, let's just write it out. So this is an Zn such that the GCD of A and N is 1. All right, and so, Euler's generalization requires some element A, so let's just let A be in there. So let A be in Zn star. Okay, so now A is some fixed element of Zn star. So then I say that Zn star is equal to A times B, such that B is in Zn star. So I'm just doing what I did before, which is multiply. Now this is all the multiples of A inside the set. So this is just the multiples of A in Zn star. And for the same reason as last time, this, yeah, so this is the claim. And it's true. So why is it true? So this is obviously going to be a subset of this set. And so if it's a subset that has the same cardinality, then it must just be the set itself. So why does it have the same cardinality? So the only way the cardinality could go down is if it turned out that A times B is the same thing as A times C mod n. So if this is true, if A times B is congruent to, this is all mod n. If it's true that A times B is congruent to A times C mod n, then you can just apply A inverse to both sides. You know it exists because the GCD of A and n is equal to 1. So then it would be the case that B is congruent to C mod n. In other words, they're the same. So that means that each element here is distinct, and so that means that the cardinality of this is just the cardinality of Zn star, so it's a subset with the same cardinality, therefore it's the whole set. Okay, so now we use basically the same trick that we did before in the proof of Fermat's little theorem. We just take the product of everything. So on the left here, I can do the product of A times B such that B is an element of Zn star. So that's the product of everything in this set. That must be equal to the product of everything in Zn star. Okay, you can factor out an n here because it's in every, it's really just a rearrangement, not a factoring, because it's a product. So there are phi of n elements here. So how many times does A appear in this product? It appears phi of n times. So this is the same thing as A to the phi of n times the product of all the elements in Zn star. And so this must be equal to the product of all the elements in Zn star. Okay, so now we just need to multiply both sides by the inverse of this. And so why does it have an inverse? It's because Zn star is closed under multiplication. So whatever this is, it's some element of Zn star, because you can't multiply your way out of Zn star. But everything in Zn star has a multiplicative inverse. That's why it's defined the way it is just to make that true. Everything in Zn star is relatively prime to n, so everything has an inverse. So you can cancel it out, and this is congruent mod n. So multiply both sides by the inverse of that element mod n, and what you get is A to the phi of n is congruent to 1 mod n. And that is the proof of Euler's theorem. So stop the video.